So hello, my name is Tsugunobu Miyake, and this presentation is about my research, developing a continuous stability meter using synchronous detection. So turbidity is a measurement that assesses how cloudy a liquid is, and it is used to assess drinking water quality. There are several units defined for turbidity, such as U.S. Environmental Protection Agency defines nepherometric turbidity unit. ISO 7027 defines formazine nepherometric unit. And those units are not related to SI units, but more of they're calibrated using formazine standard solutions. The way it's measured is that a light beam is casted on the sample, and the light intensity at 90 degrees with respect to the light beam is measured. So the idea is as the sample gets more cloudy, then more light will be scattered. And as a result, the light intensity at 90 degrees with respect to the light beam will be. So turbidity is used in several drinking water regulations or recommendations. US Environmental Protection Agency requires drinking water to be less than 1 NTU. World Health Organization also recommends less than 1 NTU for the drinking water. Water sanitation and hygiene monitoring system by UNHCR recommends less than 5 NTUs and refugee camps. However, not many regions can implement frequent water quality monitoring, and it is almost impossible to distinguish using human eyes if the turbidity is in the lower range. So here's our proposed design for the continuous turbidity meter. So this is the case. So this case clamps onto the transparent acrylic tube, which the water flows through. As you can see, the photodiode's hole is located at 90 degrees with respect to the LED hole and the laser's hole. And so we tested both LED and laser to see which one can produce a better result. And for our prototype, we used CN0363 current meter evaluation boards to collect analog input and convert it to digital signal. And we attached red LED laser and photodiode to this evaluation board. And we use Arduino Uno to communicate with the CN0363 current meter board to modulate the LED and laser, and also collects the photodiode voltage. So we use synchronous detection to minimize the effect of ambient light. So we tested both LED and laser, and that switches every 2.5 seconds. And Arduino Uno controls LED and laser. It modulates in the frequency of 125 Hertz. And the photodiode output voltage is collected at the rate of 1 kilohertz. And that is multiplied with the square wave of 1 if the light source is turned on, and -1 if the light source is turned off. And that AC signal is converted to DC signal through 1 Hertz low pass filter. So the idea is that we collected photodiode voltage when the light source is turned on and when the light source is turned off. And we are essentially taking the difference between these two raw output voltage to extract the photodiode voltage due to the light source. So to evaluate the developed continuous turbidity meter, we used Hatch TU5300 commercial continuous turbidity meter as a reference, and measures the turbidity in FNU. So the commercial turbidity meter and the developed turbidity meter are arranged such that so the water from this water tank flows through both devices at the same time. And photodiode voltage measured by the developed sensor and the turbidity measured by TU5300 are measured. So we began with 2 liters of deionized water in the tank, and we added 5 milliliters of 0.1 grams per liter bentonite solutions every 5 minutes to simulate turbidity ranging from 0 FNU to 70 FNU. And we continued the experiment until 100 millimeter solution was added. So as you can see, as the turbidity, the blue line, as the turbidity increases, the photodiode voltage measured by LED or laser also increases. The one thing to note is that the disturbance at time 4 p.m. that happened because the enclosure moved slightly due to a loose screw. And another thing to point out is that the photodiode voltage is more sensitive to the turbidity change than the commercial turbidity meter values. So for our next analysis, we only use the data for the steady state values for the photodiode. So we did correlation analysis on turbidity measured by the commercial turbidity meter and photodiode voltage measured by the our developed sensor. And we obtained a very strong correlation of R squared value more than 0.995 for both laser and LED measurements. And for LED, almost all measurements had residuals below 0.8 FNU from the regression line. We did another experiment on lower turbidity range since our interest motivation was on the drinking water applications. Instead of using 0.1 grams per liter bentonite solutions, we use 0.02 grams per liter solutions to simulate lower turbidity range from 0 to 15 FNU. And for LED, we obtained a very strong correlation of R squared value more than 0.999. With more than 95% of the data fell within 0.2 FNU from the regression line. However, we couldn't obtain a strong data for the laser. And we also performed the simulation of calibrating the sensor using 2 points calibrations. So taking 2 points that are that has different turbidity and drawing a line and estimate the turbidity based on the line. So we performed this simulation on every pair of data points that are separated by 40 FNUs. The reason why we chose 40 FNUs is because our collected data was ranging from 0 to 70 FNU, and we thought 40 would be reasonable. So the way to look at this graph is that the y-axis is the number of models or number of a pair of data points, and the x-axis is the ratio of residuals below 1 FNU for that particular model. So as you can see, most of the lines are in between 0.9 to 1.0, and that means regardless of the choice of the calibration points, most measurements, more than 90% of the measurements would fall within 1 FNU from the generated. So the conclusion is that the raw continuous stability meter resulted in more accurate measurement than previous low-cost meters, especially for the data that use the LED. And the developed meter can be calibrated using 2 points calibrations. The limitation of my research is that the photodiode output significantly depends on the sensor's orientation, as seen in the raw data graph, where the orientation changed slightly and the photodiode output voltage changed significantly. And so the calibration is necessary whenever the sensor is moved slightly. So to improve this, the sensor should be redesigned to either hold acrylic tube more securely so that we don't have to calibrate the sensor every time we take new series of measurements, or investigate single point calibration, which makes the calibration easier. So this concludes my presentation, and I would like to thank my research advisor, Dr. Marchiori, and Bucknell University for funding this research. Thanks so much.